So given any signal, you can decompose that into an even part and an odd part. So this is like saying every human has, a good component and a bad component in him. So that's like the same case for even a signal. So every signal has an even part and an odd part. So you can break down every signal, any given signal, into something which has an even symmetry and something which has an odd symmetry. So how do we do this decomposition or this breaking apart? All we have to do is take the signal as such and also take the time reversed component, take the average of it. So if you take the average of the signal and its time reversed component, you get the even part, and you take the time reversed version, subtract it from the actual signal, and then compute the average. What you get is the odd part. So why is this true? It's very simple, we can see that. So let's compute x even of minus t. What is this? So if you see, this is half x of minus t. Basically, wherever there is t, you replace that with minus t. Okay. So there is minus t here. So you replace with minus of minus t, which is plus t, which is exactly the same signal again. So which means this is satisfying the symmetry property of even signals, and hence this becomes an even signal. And do the same thing for odd. We see that we get x of minus t plus, minus x of minus t, which makes this x of t, which is equal to minus of x odd of t, and hence this satisfies the odd symmetry property. So every signal in this fashion can be decomposed into an even part and an odd part. And the most interesting property of this decomposition is that the even part of a signal is orthogonal to the odd part. So what we mean by orthogonal? It means that they are perpendicular. So what we mean by perpendicular of a signal? So if we know that given two lines, I can say that they are orthogonal. It means that there is 90-degree angle between them. But what does it mean to say that a signal is perpendicular to one another? It simply means that if you compute the area of the product of these two signals, then the area is 0. So this is very similar to taking dot product. Okay. So instead of taking dot product, what you do is you take the product and integrate it. That's all. So this is very similar to that. So you take the product of these two signals. If those signals are complex, then one of the signals you have to conjugate. Okay, this is, if you have two vectors, when would you say that they are orthogonal? You will say that, okay, I have vector x, I have vector y, I'll take the dot product. Then if the dot product is 0, then we say that the angle between them is 90 degrees, or they are orthogonal, or they are perpendicular. For a real valued signal, x star of t is equal to x of t, which means this orthogonality property just reduces to taking product and then finding the area under there. So if we're taking the product and the area turns out to be 0, then we claim that x of t is perpendicular to y of t. Okay, so you compute this product, and this product will turn out to be 0. Okay, and why is this true? There is a simple reason why this is true. Let's first see if this product itself is even or not, or even or odd. Now let's say z of t is equal to x even of t times x odd of t. Now what is z of minus t? Replace minus t here everywhere inside. If you replace, because the first component is an even component, it remains as such. The second component is an odd component, which means this is minus x odd of t. In other words, this is equal to minus z of t. So the product itself turns out to be an odd signal. This entire signal is an odd signal. Okay, and there is a very nice property that you should remember about the odd signal. The area under the odd signal is 0. So which means this integration, when you try to evaluate it, you will get 0. So you can take any signal, decompose that into even part and an odd part, and it will turn out they are orthogonal. So this is as good as saying that I can take any vector and I can decompose that vector into, an x component and a y component. That is very similar to what we are doing. So we are taking any signal and we are decomposing that into an even component and an odd component. They are equivalent, so we can take this as an analogy between vectors. So how in vectors we have orthogonality, these two components also are orthogonal. Okay, let's see some examples. So are the signals rect of t minus 1 and rect of t plus 1 orthogonal? Let's first plot them. So what is rect of t minus 1? So we know that this is the rect function, and rect of t minus 1, that is a negative, so it moves to the right. Okay, half, and this is 3 by 2, moves to the right by 1. And let's do the same thing here and plot rect of t plus 1. Obviously it's going to move to the left. We are now experts in shifting signals and even scaling them in time. This is minus half, this is minus 3 by 2. Of course this amplitude is 1. Now multiply both these signals. When you multiply both, what do you get? You get 0, right? Every point here, the corresponding points are 0, and similarly every corresponding points, they are also 0. So you multiply pointwise, right? When you multiply both the signals, you get 0, which makes these two signals orthogonal. So these are orthogonal signals. Okay, now let's check the next pair. Next pair is we are trying to check the orthogonality between the rectangular function and triangle. Remember, orthogonality means you need two signals. If I'm asking if a signal is perpendicular, given just one vector, you cannot say so it is perpendicular, right? You need at least two vectors to say that the angle between them is 90 degrees and hence they are perpendicular. So you need at least two signals to compare and then say, okay, they are orthogonal, they are perpendicular. So the next signal that we are going to analyze is the triangular function. So let's take this triangle between minus 1 and 1, okay, and amplitude 1. Now let's multiply the triangular function and the rectangular function. So what do you get when you multiply the triangular function and the rectangular function? So clearly the signal which we obtain by taking the product of these two is going to be 0 outside minus half and plus half, because the rectangular function is 0, whatever you multiply with them is going to be 0. So inside minus half to plus half is where we'll have the non-zero part, and that turns out to be nothing but so this is what we have as the product. So when you compute the area of this product, it is non-zero. So which means these two are not orthogonal. Okay, so here the area is not 0. So they are not orthogonal signals. Now, what if we had a signal which looked something like this? Let's say this is 1, this is -1, and this amplitude is -1. Okay, if we had multiplied, let's call this x of t, with the rectangular function, would we have gotten an orthogonal signal? Even without drawing the plot, we can say that yes, we'll get an orthogonal signal simply by knowing its property. This is where knowing properties actually help. This is an even signal, right? This is an odd signal. So you multiply an even signal with an odd signal, of course you get an odd signal, so the area under them is going to be 0. Okay, so even without drawing the plot, we can know that it is going to be orthogonal. We can just verify that. So what do you think the plot will look like when you multiply rect of t with x of t? Clearly, once again, only between -half to +half you'll have the non-zero components. And how are they going to look like? So you will have something like this here, and this is 1, this is half. But on this side, we have -half and -1. So the product is not fully 0, but they have odd symmetry. So because of this, the area on the right hand side is the negative on the area of the left hand side. So if you compute the area here, the area is going to be 0. So x of t and rect of t are orthogonal signals. Okay. All right. Now let's see some more interesting examples. So remember, sinusoid was one of the standard signals that we encountered earlier, and we'll keep encountering sinusoid often again and again. So we should know more about the sinusoids. So what about cos omega t and cos vt? Are they orthogonal? So let's try and integrate and see. Okay, so omega is some angular frequency and v is some other angular frequency that is given to us. So how would we integrate this? So we'll use the regular formula, this cos A cos B formula, and then we'll just simply say that this is integral of plus okay. Now what is the value of this integral, which is from -infinity to +infinity? So if you think about this, of course it is an even signal because of cos, so we'll get this to be just 2 times of the area between 0 and infinity, and hence we have the same thing, but the limits are now changed. Now what is the area under the cos curve from 0 to infinity? So when you plot it, how does cos look like? So this is what we have. So if you see here, let's take 1/2 of a cycle. So in 1/2 of a cycle, the area here is positive and the area here is negative. So the total area in this 1/2 of a cycle is 0 because they are exactly equal to one another. Similarly, if you compute in the next half cycle, this area is once again 0. So you can divide the entire portion on the right hand side into multiple half cycles, and every half cycle you will have area equal to 0, which means this entire area is 0, and similarly this entire area is 0. So the total area under this curve is 0, which makes these two signals orthogonal. So given any two sinusoid, any two cosine function of frequencies omega and v, they are orthogonal. Now what if omega is equal to v? So that is an important case that we have to think about. So let us say that omega is equal to v. If omega was equal to v, then this integration here will have cos of 0 times t, or cos 0. Cos 0 we know is 1. So this value will go to infinity. So when you take this integration, this will go to infinity, which is not 0. So an important thing to note is this is orthogonal only if omega is not equal to v. If omega is equal to v, then we say that they are not orthogonal, because if omega is equal to v, it's the same signal, right? So a vector cannot be orthogonal to itself. That's exactly what we are saying. So cos omega t is one signal. It cannot be orthogonal to itself when v is equal to omega. So it can be orthogonal to any other sinusoid. So given any sinusoid, it is orthogonal to all other sinusoids. So this means that even if I take a sine, it should be orthogonal with cos. Is that true? Let's check that. So sine omega t times cos vt. You know what, we are not even going to evaluate this integration because this is 0 for the reason that cos is even, sine is odd. So the entire product is odd, and this is just 0. So which makes all sine and cosine functions together to be orthogonal to one another. So this is a very nice property that we have here. Okay, so any sine and cosine together are going to be orthogonal, and any sine and sine or cos and cos, they are going to be orthogonal as long as they are of different frequencies. So if somebody gives you a bunch of sinusoids, as long as they are all of different frequencies, you can safely say that they are orthogonal to one another. This is a very nice property of sinusoids which we'll use often and often later, that all sinusoids are orthogonal to one another. Okay, this is a very important thing to keep in mind. Now these are all real valued sinusoid. What if we have a complex sinusoid? Remember we saw complex valued signal earlier, and e power j omega t is complex sinusoid. Now what about those? Can we comment anything about that? So let's look at that. So we have e power j omega t and e power minus j omega t. Okay, so are they orthogonal? Let's take e power j omega. This is complex. So because it is complex, remember we have to take the conjugate of one of these complex valued signals. We will take the conjugate of minus j omega. It doesn't matter what signal that you are conjugating, it could be either one of them. So what is this? So this is e power j omega t times e power j omega t itself. Okay, so this is just okay. Now how do we evaluate this integral? So it's not very difficult to actually evaluate this integral, because we know that e power j2 omega t is equal to cos 2 omega t plus j sine 2 omega t. So we can just substitute that here. Okay. So substituting that here, we will get this integral to be cos 2 omega t, which is 0, plus j sine 2 omega t, which is also 0. Okay. So this area is 0 and this area is also 0, which makes these two signals orthogonal to one another.